All right, so in the previous video, we introduced the cross product of two vectors in R3, and we also discussed some interpretation of those, some useful theorems surrounding those. One, the cross product of two vectors always produces a third vector that's orthogonal to both of the vectors that we took the cross product of in the first place. And we also showed how the magnitude of the cross product relates to the angle between two vectors, and how we could use that result to show that the cross product of two parallel vectors is the zero vector. But in addition to that, we have some more useful geometric interpretations of what the cross product, and specifically the magnitude of the cross product, actually represents. So let's suppose for a moment that A and B are two non-parallel vectors. Then you can see from this diagram that they determine a parallelogram. If we have their initial points coincide like this, and then if you were to copy A up here and copy B over here, you create this little parallelogram. The magnitude of A cross B happens to be equal to the area of this parallelogram. And here's the argument for that. If you remember from geometry, the area of a parallelogram is its base times its height. Okay, so by dropping a perpendicular from this terminal point of B down to A like this, we can see that we have this right triangle, and it's relatively straightforward to show that the magnitude of B times the sine of this angle would give me the height of that right triangle. But that's also the height of this parallelogram. What is the base of this parallelogram? Well, that would be the magnitude of A. So that tells me that the area of this parallelogram is the magnitude of A times the magnitude of B times sine of theta. That would be the height. Looks like this. However, we just showed in the previous video that this is equal to the magnitude of A cross B. So let's look at an example where we want to use a couple of these properties that we showed surrounding the cross product. So first of all, this one says we want to find a vector that's perpendicular to the plane containing these 3 points, P, Q, and R. Okay, so let's imagine P here, Q here, R here. This is something that we have to do a lot of in 12.5 and onward, because it turns out, as we're going to see in 12.5, that if you want to determine the equation of a plane, you need two things. You need to know at least one point in that plane. We have 3 here to choose from. But you also need to know a normal vector to that plane. A normal vector is a vector that's perpendicular to that plane. Or in other words, it's perpendicular to all vectors contained in that plane. We'll talk more about that in 12.5. But what we need to do now is think if these points are in 3 space, so they're in 3-dimensional space, some plane contains all 3 of them. That's always going to be true of 3 points in space. I need to find a vector that's perpendicular to that plane. Well, one way to do that is to form vectors out of these. So for example, if I found the vector PQ, how do you find the vector PQ? Well, in component form, we know that that comes from subtracting corresponding components. -2 minus 1 would be -3. And then 5 minus 0 is 5. 0 minus 3 is -3. What about this vector QR right here? In component form, that would be 2 minus -2 is 4. And then 2 minus 5, which is -3. And then -2 minus 0, -2. Okay? Now, if I were to take these two vectors and evaluate their cross product, then the result would be a vector that's perpendicular to both of these simultaneously. We proved that to be true of the cross product of any two vectors. But if you can imagine we have this plane here. Suppose one of my vectors is right here and the other one is right here. The cross product gives me something that's perpendicular to both of those vectors, and you can kind of see from this picture that that result would be perpendicular to the entire plane as well. So this all just boils down to evaluating that cross product. I want PQ cross QR, which is equal to IJK then the components show up in the rows. -3, 5, -3, 4, -3, -2. I'm going to bypass all of the work since we've done an example already and go straight to the answer. We end up with -19i minus 18j minus 11k. This vector is perpendicular to that entire plane. Now, something that's worth noting, I could have approached this slightly differently, still using the same approach of doing a cross product, but I could have found different vectors here, right? I could have done PR and PQ or QP, or there's different variations on this, which would have given me different vectors, and I could have taken the cross product of those vectors and gotten something that looks different. So does that mean that I have to choose these in a specific order to get a right number? The answer is no. And the reason for that is because there's more than one right answer to this. Notice that this vector, if I make it longer, its components will look different, but it's still orthogonal to the plane. Or if I flip it around and have it point downward instead of upward, the vector would still be orthogonal to the plane. It's just pointing in the opposite direction. That's fine. So there are more than one answer to this question. But one thing that's interesting to note is even if I formed these vectors differently, PR and QP instead of these two, found their cross product, the result should be a scalar multiple of this. And the reason for that is you can see that any vector that's perpendicular to this plane would have to be parallel to the vector that I already found, meaning some scalar multiple of it. So it might be worth running through this problem in a different way on your own and seeing that fact yourself. Okay. Next thing we want to do, find the area of the triangle whose vertices are the points given in the previous example. So we have these 3 points, right? And we formed vectors out of them. But notice they do create this triangle also. Whoops. Let's suppose that these are the 2 vectors that I created, though. If you notice, if I were to form a parallelogram from these 2 vectors, the triangle that I'm interested in is exactly half of that parallelogram. And we found a formula for computing the area of a parallelogram up here. It's just the magnitude of that cross product. So I'm lucky here because I'm using vectors that I've already computed over here. I've already found the cross product of these guys. That means all that I need to do is find the magnitude of this vector and then cut it in half, because this triangle is half the parallelogram that I would be finding. So A is equal to 1/2 times the magnitude of -19i minus 18j minus 11k, which is equal to 1/2 times the square root of -19 squared plus -18 squared plus -11 squared. That goes right into a calculator. We get a decimal for this one. It's approximately 14.195. Okay? Interesting little application. This allows us to find areas of triangles that are floating around in space, as long as we happen to know the coordinates of its vertices. Nice little application of this. All right. So one thing that I did mention before was that we were going to take another look at why the cross product happens to not be commutative. And an interesting application of, or an interesting way to see that is if you take cross products of the standard basis vectors. So I cross j turns out to equal k. You take the cross product of these 2 standard basis vectors and you happen to get the third one as a result. You can prove this to yourself by thinking of the components of all 3 of these vectors and verifying it. Look at what happens if I reverse the order of I and j, though. J cross I is -k. And that shouldn't be a surprise because we talked about the right-hand rule. If you reverse the order of these 2 vectors, then instead of having my hand face, upward, I have to turn my hand around and have it face downward so that my fingers curl in the opposite direction. So this again shows that the cross product is not a commutative operation. However, it's close to commutative, which we see in the first property listed here. If I have A cross B and I go and reverse the order of that, I get the opposite of A cross B. So A cross B is equal to negative B cross A. They're related, just not equal. Okay? There's a few other properties here which I'll let you look over. This basically these properties are what allow us to do some algebraic steps in expressions involving cross products. We do have sort of a version of the distributive property, for example. Cross products is distribute over sums of vectors in both directions. Dot products and cross products have a way of interacting with each other, which you see here. This one is a lot less, this one might be a little bit more surprising, but all 6 of these properties hold when dealing with cross products. There's a proof of one of them here, proof of 5. I pulled this out of the book because this particular property is going to imply something that we're going to look at in a moment. I'm not going to walk through this again because it's just really heavy algebra, and it's using the definition of the dot product and the cross product, and then doing a lot of algebraic simplification to get from here to here. But what I do want to point out is this particular combination of operations here. We're using a dot product with a cross product. One thing you would need to ask yourself anytime you look at something like this that's using a combination of more than one operation is whether or not that thing is defined. Back in 12.2, we showed that you can't take the dot product of 3 vectors at once. A dot B dot C, it doesn't make any sense, because ultimately what you're doing is you're trying to dot a scalar with a vector. Here, this makes sense because B cross C is a vector, and A is a vector, and we can take the dot product of 2 vectors. The result will be a scalar. What would not work is if I swapped these two. If I said A cross B dot C, well, the parentheses we would deal with first, and B dot C is a scalar. You can't cross a vector with a scalar. So you have to pay much more close attention in this sort of context as to whether or not the operations you're doing actually make any sense at all. But that said, this particular product is an important one. We call it a scalar triple product. The result is going to be a scalar, and it's always of this form, A dot and then in parentheses B cross C. So what is the relevance of a scalar triple product? Well, one thing that I'm not going to walk through the algebra to show you, but actually does become apparent if you study this proof, is that this scalar triple product can be evaluated just as a single determinant. Remember, when you evaluate the cross product of B and C, the evaluation looks like a determinant where B and C show up as the second and third rows. Now notice in this determinant, though, the I, J, and K have been replaced by the components of A. If you go back, like I said, and look at that proof of property 5 on the previous page, you can see with some algebraic know-how why this is true. But we're just going to be using this fact for calculation. All right. So again, we call this thing a triple product, and it turns out that it too has a geometric interpretation. So this figure right here is something that we call a parallelepiped. You may not be familiar with that term, but a parallelepiped is a three-dimensional solid, all of whose faces are parallelograms. And any 3 vectors in R3, any three-dimensional vectors, will determine a parallelepiped provided that they aren't coplanar. Coplanar meaning they all lie in the same plane. So you can see, for example, B and C lie in the same plane, and that plane contains the base of this parallelepiped. And A kind of rises above that plane and gives some height to this parallelepiped. But if A was coplanar to the other 2 vectors, then we can imagine bringing the tip of A down into that plane, and it would collapse this 3-dimensional solid into a 2-dimensional face, which would not be a parallelepiped anymore. So assuming they're non-coplanar, we can always get this 3-dimensional solid called a parallelepiped. All right, now what do we do, or what are we doing here? Well, how do you find the volume of a parallelepiped? It's the same way that we find the volume of any prism type shape. It's the area of the base times the height of the object. And the height of this object, if you look at the way things are labeled here, can be found by thinking of the cross product of B with C first. Again, remember, B and C determine this base for this parallelepiped. The cross product of B and C would be a vector that's perpendicular to that base. And we need a perpendicular vector or line segment in order to determine the height of this object. And so that means the height can be found by comparing it to B cross C. Now, if we look at B cross C, it appears to form an angle with this edge here formed by the vector A. So let's call that angle theta for a moment. We see that this creates a little right triangle, and using similar techniques as what we've seen before, we can find the height of this thing by thinking about this right triangle. The height is going to be, I wrote it in here somewhere, the magnitude of A, which is like the hypotenuse of that right triangle, times the cosine of that angle theta. And you should be able to see why that's true, even if you kind of work it out off to the side. What about the area of the base? Well, the base is a parallelogram, and that parallelogram is determined by these vectors here, B and C. We just saw a little earlier that the area of a parallelogram determined by two vectors is the magnitude of the cross product of those two vectors. So magnitude of B cross C. Putting those things together, the volume of this parallelepiped is the area of the base times the height, except the area of the base we found was the magnitude of B cross C, and the height was the magnitude of A times the cosine of theta. Now think about this for a moment. What we have is the magnitude of two vectors times the cosine of the angle between those two vectors. Here's where we see those two vectors. We know from section 12.3 that this thing actually represents the dot product of A with B cross C. A dot B cross C. Now the only thing we need to be careful of is, which wouldn't occur in this specific example, but in a different example, remember the dot product can come out negative. So because volumes are meant to be positive, we can take an absolute value here to ensure that that happens. This is an absolute value, not a magnitude, because this dot product in here would be a scalar, not a vector. Okay, now there's one interesting implication of this. Remember, I said that this little derivation sort of depends on A not being coplanar to B and C. But if all three vectors were coplanar, and then based on that argument we made before, this parallelepiped would collapse down to just a parallelogram, a two-dimensional figure instead of a three-dimensional figure. That two-dimensional parallelogram would have zero volume. So what does that actually imply? Well, it gives us a technique for determining whether or not three vectors are coplanar. And all we need to do is evaluate their scalar triple product. If that comes out to 0, that implies that the volume of that parallelepiped is 0, which could only occur if all three vectors are coplanar. So as a final example for this section, let's see if we can determine if these three vectors shown here are coplanar. I want to take their scalar triple product, but as we saw up here, we can use a 3x3 determinant containing just the components of these vectors to show that. 1, 3, 0, negative 2, 2, 1, negative 1, 5, 1. Okay, this determinant would equal 1 times 2, 5, 1, 1, minus 3 times negative 2, negative 1, 1, and 1. And here I don't need to write the last part. 0 times anything is just 0, so that's not going to contribute anything useful. This becomes 2 minus 5, which is negative 3 times 1, that's negative 3. Here I have negative 3 times, this becomes negative 2, minus negative 1, which is negative 1, so negative 1. That's negative 3 plus 3, or 0. That's what we were looking for. That scalar triple product came out to 0. Therefore, all three of those vectors have to be coplanar. And that's going to wrap up 12.4.